that I ran into just before the lecture told me that, yeah, so just organization-wise. So first of all, this part of the lectures will have absolutely zero to do with the first. So if you weren't here or you didn't understand anything of the first lectures, it's okay, because we're going to do something completely different. The second thing is that I noticed that there's no Q&A tomorrow, because you guys are going to see and learn about Galileo and go up the hills or something like that. So, so if you want to stay after this lecture, yeah, because on Wednesday I'm leaving right after lecture, so there's no time then either. So if you want to stay after this lecture and ask questions about whatever. So, oh, thanks. Good. So, maybe I should ask, are there any questions at all? No. Very good. So then what we're going to do for this part, so these 3 days, we're going to be discussing black hole thermodynamics. And as you well know, this is a very, very famous and deep subject between the relationship between gravity, thermodynamics, and the quantum theory. And this subject is really important. So all the progress that has been in quantum gravity in the past 40-something years is based on this subject. So in principle, I guess all of you know pretty much what it says, you know, black hole entropy and all of that. Yeah, so it is an old subject. This is what I was telling these guys. It's in no sense advanced, so probably shouldn't have been in the school. It's stuff, so I'm going to be talking about stuff that was developed in the 60s and 70s. Yet I think it's something that's nice to know, maybe in a little bit more detail than what you might hear. So I just hope that it's going to be useful. So basically what I will do, I will just follow the historical route that the subject was developed, and that was started with the singularity theorems. A work by Penrose. Okay. But basically the sort of the essential idea that got this thing started was the demonstration by Penrose that singularity formation. So it was known at the time that you have singular space-time solutions, like singular cosmological solutions, Friedman, Robertson-Walker universe with a Big Bang, and then you also have the spherical symmetric Schwarzschild, which has a singularity at r equal to 0. But it was certainly not appreciated at all whether if you started destroying the spherical symmetry, whether the singularities would still form or they're just an artifact of the symmetry. And it seems that Einstein himself believed that if you add some rotation and something, then you have ways to avoid the singularity, as you can, for example, in Newtonian mechanics. In Newtonian mechanics, if you collapse some particles that in a perfectly spherically symmetric way, they would have a singularity at r equal to 0. You make them rotate a bit and do stuff, and they avoid each other, and that's no problem. So basically, this subject was basically started with this work by Penrose on the inevitability of the formation of singularities in gravitational collapse, the fact that it's a generic phenomenon. And I think it's a particularly nice time to talk about this work because, as you probably know, he got the Nobel Prize for this work last year. Just to make sure we're, just a little test. So if you guys were astrophysicists and you're looking and you're seeing some massive objects, how do you determine whether that massive object is a black hole? Not LIGO physicists, just astrophysicists. What do you look for?
They're black.
How do you see whether something is black?
I can't see it.
Yeah, but I mean, it should be not only black. You can stare into empty space and that's still black, right?
Gravitational lens.
Very good. So they should have a mass. So if you look around these objects, you can look at, for example, stars orbiting the object, and then you see that it's like that. There's that black thing in the middle looks like it has a very big mass. You can determine from the orbit. So this is what they did for the black hole in the center of our galaxy. But still, so suppose that your the orbits of the stars don't get more than a few tenths of Schwarzschild radii closer to the black hole. How do you know that thing is a black hole or something else? Some other, some sort of neutron star, some sort of very, very compact state of matter.
You can show certain stars can't, like neutron stars can't be as big as black holes can be.
Exactly. So the only way that so the main way, and actually this woman, Andrea Ghez, who also got the Nobel Prize last year, the astrophysicist, so she gave a talk at UPenn like a few years ago, and I asked her, like, how do you guys know? Because they can't get close enough to the black hole to really see that, to really probe the geodesic motion close to the black hole. And the way that they know is that anything that's black and compact and its mass is greater than 3 times star is assumed to be a black hole. And that comes from the fact that you simply cannot hook up how do you say, an equation of state for matter that would sustain a mass bigger than this. So you have something called the Chandrasekhar limit. Is it the Chandrasekhar? Am I getting this right? So you have the Chandrasekhar limit for white dwarfs, which is m has to be smaller. So if the mass is greater than 1.5 solar masses, then that compact object cannot be a white dwarf, because it's simply that the equation of state cannot withstand a bigger mass. And for a neutron star, this is the limit. Okay? So anything that you look up in the sky that's compact black and has a larger mass than this is a very good candidate for a black hole by basically exclusion. And this is how you see that this work of Penrose is showing that singularities inevitably form generically, and then there's cosmic censorship, which tells you that generically singularities always form if certain conditions are satisfied in gravitational collapse, and then there's cosmic censorship, which tells you that generically they're going to be cloaked by a horizon. This is how you know that most of the things over there are actually. So just to tell you that this has a really big, experimental, which is why I guess it was recognized. Okay, so so I'm going to discuss a bit. So the work is kind of mathematical. So I'm certainly not going through the main in all of the details. So I'll just give you a flavor about what he did. And at the end of the day, what you see is that he did what he proves is it's kind of it's very. He doesn't prove that there's a curvature singularity, that the curvature scalars blow up or anything like that. Actually, in his work, it's not very clear what the nature of the singularity is. He just shows that certain geodesics cannot be extended past a certain point. So it's a sort of a very indirect kind of approach, but it's power lies in its generality, and in the fact that he introduced some very useful concepts to study this problem, which is the notion of trapped surfaces, which is basically a local condition to determine whether you're going to eventually have a singularity, and by cosmic censorship, therefore a black hole, and also introduced a lot of the idea of dynamic horizons and studying things like this. So it's some very ingenious work. Okay, so let's stop lying and actually get to it. So let me start by talking about gravitational collapse.
Sorry,
yes.
I don't think the mic is working correctly.
My mic. Do you hear me at all?
Yeah, we can hear you, but it's not very clear.
It's off. Huh? Yes. It's off. Now is it better?
Yes, thank you.
On the other hand, now I hear myself really badly. Can you just put down the volume? Hello? Do you guys hear me now?
No. Yes, we hear you.
We hear. Oh, okay, then it's perfect. Yeah, perfect, thank you. Okay, good. So did you hear anything of what I said? Okay, good. So we're doing gravitational collapse, and for simplicity, we're just gonna consider collapsing a spherically symmetric collapse, which is particularly easy to treat because we know that, so suppose you have some star, which is collapsing in a completely spherically symmetric way. And then the point is that outside the star, so you're solving which equations? The vacuum Einstein equations, because you're outside the star, and it's spherically symmetric, and therefore the metric is? The metric is Schwarzschild indeed, and that follows from the so-called Birkhof Theorem, which shows that spherical symmetry plus the vacuum Einstein equation implies staticity. So this is the metric outside. Okay, so for R smaller than R star. Okay. And now I just told you that if the mass of the star is bigger than 3 solar masses, actually you cannot halt this gravitational collapse. And it's just going to collapse all the way to the end. And therefore, well, at some point, so once the radius of the star becomes smaller than 2m, you're just going to get a horizon, which is at r equals to 2m. Now, so you're going to get a black hole. Before going on, maybe I should remind you, or maybe you can remind me, what is a black hole? Is this too interactive? I can make it less interactive if you want.
It's a causally disconnected region of space.
Okay, very good. So black hole, maybe one can rephrase it. So it's a part of the space-time from which one, more speaking, cannot escape to outside. And in order to define that outside, it's good to have some notion of infinity. So we can use, for example, an asymptotically flat space-time to define our notion of infinity. So, so the black hole region, which I'm going to call B, of an asymptotically flat space-time, maybe I should, of an asymptotically flat space-time is in asymptotically flat is your manifold minus the causal past of future null infinity. So this is a J, and this is a curly I, which looks like a J. What am I going to do? Scri plus. Okay? So here you have your Scri plus. Okay? And here you might have your black hole. So, so if you're looking, you start from Scri plus, and then you go along path-directed causal curves into your space-time. You may cover the entire space-time, like, for example, if you're in Minkowski space, you start from here on all possible path-directed causal curves. You're going to recover the entire space-time. Or, if you're having a black hole, whose Penrose diagram, let's do a black hole from collapse, which looks something like this, right? Is this too fast? You've all seen a Penrose diagram of a black hole, okay? So here you see that the causal path of Scri plus is basically this region. So the black hole is basically this region, okay? And the horizon, the future event horizon, H, is the boundary of this B. So it's basically this, there's no yellow. It's basically this guy. And by definition, H is a null surface, hypersurface. Okay. So a comment which I'm sure you know is that the horizon cannot be determined locally. So when you fall, when you're falling into the black hole, you don't realize that you're falling inside the black hole. You must know the entire future evolution of your space-time in order to determine how the horizon, where the horizon is. And this you can see clearly from the definition. I have my space-time, I go to Scri plus, and then I'm trying to go back in the past and see where this H is. Okay, but I must know all the future evolution. Okay, good. So that's the black hole. So now coming back to our gravitational collapse. So now we want to go past this surface at r equal to 2m.
Can you make an
Yeah.
So you're saying that the null condition of the area surface is not a local condition?
I'm just saying that locally, you cannot determine where the horizon is.
But yeah, if I am in a point of the horizon, I should be able to determine whether the surface is null, is like or
You can. I mean, you can find a null surface. You can certainly find a null hypersurface. But you cannot know whether you'll be able to get out of the black hole or not.
Okay.
Yeah. So, and actually, in a second, we're going to be discussing local conditions, which oftentimes they will coincide with the horizon, but not generically.
So not all the null hypersurfaces are horizons?
No, it's this guy.
Okay.
It's the boundary of it's the boundary of the causal path of Scri plus. Yeah. It's a very, very particular null surface, but it's important that it's null. So a lot of the manipulations that we're going to be doing have to do with the fact that it's use very, very essentially the fact that it's a null hypersurface. Very good. So now we want to pass this r equal to 2m surface, and as you well know, this Spatial coordinates break down there because this term blows up. So we have to go to some coordinates that are good through the horizon. For example, Eddington-Finkelstein coordinates. And in order to do this, so basically what we want to do, we want to cross this horizon along sort of ingoing null rays. So we need to write the metric in some appropriate way. And we're going to write it like this: 1 minus 2m over r dt squared minus dr star squared. R star, did I call it R star? Yeah. Plus r squared d omega 2 squared, where r star is called the Tortoise coordinate, and it's defined via this relation. So you see that dr star equals to dr over 1 minus 2m over r, right? And when you integrate, which implies that R star is, what do you get? R plus 2m log of R minus 2m. Okay? So you notice that as R goes to 2m, R star goes to minus infinity. Okay? So basically what you do, you introduce a new coordinate, little v, which is t plus R star, which is called advanced Eddington-Finkelstein time. And you're going to basically be keeping this little v fixed as you're going to cross the horizon. So that basically means that you're sending t to infinity. R star, we agreed that is going to minus infinity with this guy fixed. Okay? So now if I'm to write this part of the metric in terms of dv, so t is dv minus dr star, so this is dv minus dr star squared minus dr star squared. Therefore, I get dv squared minus 2 dv dr star. And then this is really not a good place to write. Okay. Then I'm getting basically that ds squared is minus 1 minus 2m over r dv squared minus 2 dv. Dr star times that prefactor is just dr, as you see from here, plus r squared d omega 2 squared. Okay? So this is basically the Schwarzschild metric in Eddington-Finkelstein coordinate. And you see that in this coordinate system, the metric becomes perfectly smooth at r equal to m. So using this, you can just analytically continue your metric through the horizon. And the only true singularity, is, as you know, is at r equal to 0. Okay? So now, maybe I should ask, how many people have not seen this in their GR course? Okay, very good. That's what I thought. Good. So now what one would like to do is to study the behavior of light cones as one crosses the horizon in this coordinate system. So if I'm just in Minkowski space, so I have T and R. So I'm considering some spheres of radius R and their evolution in time. So if I'm sitting at some R0 and I'm shooting some rays of light, so if I'm sitting somewhere, I can, in Minkowski space, I can shoot my ray of light radially that way, or radially out or radially in, which would basically correspond to this or that. Okay, so everything will move with the speed of light. So this is why at 45. And you see that the outgoing light rays, so they're going to go to increasing R, and these guys to decreasing R. Now, so this is in T and R. So this is my light cone. Now, if I, so here is R is R naught plus or minus CT. Now, if I want to write this in terms of this V and R coordinates, then what I'm going to get, and let me forget about the R naught, then I have, and let me set C to 1. So for the in guys, so R is minus T, so you see that R plus T is 0. Whereas for the out guys, R is T, so you see that V is 2R. Okay, so if I now draw this coordinate system, where I write V and R over here, then one guy is going to be at V equals to constant, this guy, whereas the other guy is going to be at V equals to 2R, which looks sort of like this. So this is how my Minkowski light cones look in this funny coordinate system. This funny coordinate system, sorry, just to write Minkowski in this funny coordinate system, I set m to 0. And we've already discussed this in terms of retarded time. We've discussed this quite a bit in the case of asymptotically flat spacetimes and so on. Okay, good. So now we want to study the behavior of light cones in this coordinate system in the black hole geometry, which is this. And basically what you see happening is the following. So asymptotically, of course, your light cones are just going to be this, because asymptotically you're Minkowski. Okay? And then as you're going in, then you're seeing that this guy, the outgoing guys, are becoming closer and closer to the vertical, to the point that here, they're just going to become like this as you cross the horizon. And then you're becoming even closer. Of course, there's the guy on the other side. I should draw it. How do you see this from this metric? So we're looking at null geodesics in this metric. So let's fix the let's fix theta in phi, so we don't care about this term. So in order to get the s squared equal to 0, you see that it's either v equal to constant, which are basically the ingoing guys, or 1 minus 2m over r dv plus 2 dr equal to 0, which is the other guy. You can check that I got the sign wrong. How did I get the sign wrong? Wait. I got the sign wrong because there was an overall minus sign. So I got a relative minus sign, but there was an overall minus sign over there, so this is a plus. Okay, very good. Okay, so the light rays that we're looking at, so the ingoing geodesics are just these guys, which I've drawn over here, whereas the guys determined by this, you see that once you pass, so if we compute dv by dr, for the outgoing guy, it's 2 over 1 minus 2m over r. So you see that asymptotically, when r goes to infinity, this is just 2. So this is the Minkowski result. But then, once r decreases to 2m, so this thing goes to infinity, and then it becomes negative. Okay? So basically what this means is that all causal curves that have to lie inside these light cones, well, now they're forced to go to the r goes to 0 singularity, and they're going to do so in finite affine parameter. Another thing that you can notice from this picture is that you see here the area of the light front, for example, in Minkowski space, for the outgoing guys was increasing, whereas for ingoing guys it was decreasing, but that's fine. But for the outgoing guys was decreasing. What's happening once you pass the horizon, both the ingoing and the outgoing guys, the area of the light front shrinks for both of them. Okay, is it clear? And the reason that this is happening is basically that, as you well know, the gravitational field has a focusing effect. So that's the usual bending of light. And once you get behind the horizon, the focusing effect is so strong is that all the light rays just do like this. They just go in. And this is basically sort of a local manifestation of the fact that you have a horizon, that these guys will never escape out to infinity. Okay? So, and, okay, so this sort of behavior is the basic intuition behind this construction by Penrose of the notion of trapped surfaces. Which are basically some space-like, smooth space-like compact surfaces, which have the property that both sets of null geodesics that are perpendicular to them have converging light front. Okay, and okay. So that's basically a local criterion. So with regard to the question that I had, so this is one way that locally you could be able to tell that you're inside the horizon. And I think you know, numerical people when they're looking for like formation of black hole horizon and so on, this is what they check for, is the formation of trapped surfaces, and that's a completely local criterion. The boundary of the region that contains the trapped surfaces is called the apparent horizon. So the boundary of the region with trapped surfaces is called the apparent horizon. And you know, in this particular case, it coincides with the event horizon, but it need not to. So in particular, this guy doesn't need to be a null hypersurface. And just to give you a simple example of the difference between the two, so suppose you have some star that collapsed, and then okay, it formed some black hole, but then at some so you have some star of mass m over here, and then you send later. Later you send some additional matter with mass delta m. Okay, so basically what's happening here is that so the event horizon on the Penrose diagram, the event horizon is still going to be at 45 because it's a null hypersurface, and all null lines go at 45. But what's happening with the trapped surface is that the apparent horizon, so before the mass shell hits, was sitting at r in spatial coordinate, was sitting at r smaller than, so r equal to 2m. It's the boundary of the region with trapped surfaces. So r apparent horizon. Whereas after the mass shell comes in, the radius of the region, so the horizon, it's not that the horizon moves, but so the radius of the apparent horizon, okay, it's going to go to 2m plus delta m, right? So locally, what you have, so the apparent horizon, basically what it does is something like this. So here it coincides with the event horizon, but here there's a jump because of this delta m. So it's not necessarily a continuous surface. It's a less nice thing to consider. But it's a very useful local criterion, and okay, and this is what yeah, that people use quite a bit. Now, one of the nice thing about this notion of a trapped surface is that you absolutely don't need spherical symmetry to define it. You're just asking a criterion of convergence on the null geodesics perpendicular to these surfaces. That can be done, for arbitrary surfaces and arbitrary geometries. So there's no problem. And basically, it's from this concept that he started out to prove his singularity theorems. So now what we're going to do, we're going to discuss trapped surfaces a little bit more generally. And for that, we need to discuss congruences of geodesics and how they behave and so on. But basically, what I want you to get from this sort of textbook example is that the basic intuition just comes from this simple study of the Schwarzschild black hole, is that the light cones tilt, and that's a local criterion for the existence of the black hole. Any questions? If there are no questions, let me talk about congruences.
Sorry,
Yes.
a clarification regarding the terminology, because before you defined the beginning black hole as the interior, let's say the region of your space-time, which is disconnected from.
Yeah. Such that signals don't make it out to infinity.
And you define your horizon as the boundary of this of the black hole, so it is codimension 1.
Exactly. It's a null hypersurface of codimension 1.
But the apparent horizon is the boundary of a surface.
Yeah, but then you have to sort of evolve it in time.
Okay.
Right? So for each spatial slice, so here you have your black hole. So you can take some space-like surfaces, and for each of them, you can determine what the geodesics are doing and where do they start converging. And for each slice, you're going to get some boundary of this region. So suppose I'm not even drawing the horizon. I'm just looking at here, here, here. Here is where they're starting to all converge. And then I just draw some line through. Here is just that, as I showed in that example, this thing can jump if you start throwing. And this should also make it clear why you cannot locally determine where the event horizon is, right? Because locally you can just determine where the ping guy is. Like before the delta time arrives, you can determine where the ping guy is, but you see that the horizon is out. Okay, good. Okay, so what is a congruence? A congruence is just some set of curves in some open region of space-time such that they don't intersect. And now we want to consider these curves to be geodesics. And moreover, we want to study the time-like case first. So for the black hole applications, we'll need congruences of null geodesics. But just to warm up, we're going to do time-like. And as you'll see, the time-like geodesics are already fun. Okay, so we're going to consider geodesics. And they're going to have some tangent vector, xi mu, which is dx mu by d tau. Tau is the proper time that's parameterizing the geodesics. And they're normalized. Okay, so that fixes the parameterization. Then you want to define a tensor field, b mu nu, which is d nu xi mu. And this guy is interesting. So first of all, you can show that it's purely spatial. By which I mean that if you contract any of its indices with xi mu, you get 0. So let's see how that works. So xi mu b mu nu is xi mu d nu xi mu. Can anybody say why this is 0? How should I write this? Xi mu, d nu, xi mu. This is a true fact. And now, right? The metric is, I can pass it through the covariant derivative. And this guy is nu of xi squared. And because xi squared is -1, this thing is 0. Okay? So this is 0. Then I also want to do xi mu sorry, xi nu b mu nu, right? Because b mu nu is not symmetric. And this thing is xi nu b nu xi mu. Hint.
It's parallel to itself. It's parallel to itself.
Yeah. So the thing is a geodesic. And basically this one is just the geodesic equation. It parallel transports itself, so this is zero. So this is how you see that this B has no spatial components in the sense that it's perpendicular to this sort of time-like vector field. Then what do I want to do? Then, just to understand a little bit what this guy does, it's good to consider some other vector, eta mu, which is the infinitesimal displacement vector. Okay, my use of the board is terrible. Okay, so basically here, what do I want to do? So here I have my xi mu, right? These are my curves xi mu, and then I want to consider some other vector field which basically tell me the displacement between two nearby curves. Okay, you might have discussed this when you discussed the geodesic deviation equation. This is what you look at, and so basically you want to call these curves. Okay, so these curves. All of these curves, the vertical lines, I'm going to call gamma s of tau. So they have their parameterization, and S labels the curves. And this eta is basically d by ds. It displaces me between the two nearby curves. And basically, the fields xi mu and eta mu commute, because one is basically d by d tau, and the other one is d by ds. So their d bracket is 0. Which is basically this equation. D mu xi nu. Okay? But now, you see that this d mu xi nu from here is nothing but eta mu b. So the second the mu is the second guy. So it's like this. Okay? Okay, so basically what you see is that this b nu mu is basically telling you about the failure of this displacement vector to be parallel transported along C. Right? This is what this equation. If this were 0, it would be parallel transported, but it's not. Okay, so it's basically telling you about the behavior of this geodesic congruence as you go along it. Then another thing that you want to define is the spatial metric. H mu nu, which is just G mu nu plus xi mu xi nu. Basically this projects you on the surfaces that xi mu is perpendicular to. And now what we want to do, we want to decompose this b mu nu in some sort of meaningful way that we can sort of interpret physically. It's not even physically, it's geometrically, if you wish. It's all about, you know, the geometrical behavior of what these geodesics do. So you want to define the expansion, which is called theta, which is just the trace. So the reason that I'm taking the trace this way is that, as I show you, this guy is purely spatial, and similarly is this guy. So in a certain sense, this is a three-dimensional tensor, and this thing equals d mu xi nu. So basically what this measures is the average expansion of nearby geodesics. Okay? If they do like this. And actually you can relate this to, if you're taking some bunch of geodesics and looking at how the transverse area is changing, so the square root of the determinant of H, how it's changing as you go along, basically you see that the expansion is nothing but A dot over A, where the dot is just d by d tau. Okay, so this is telling you how the cross area is changing. Then you define the shear. We're gonna care less about this. The shear is sigma mu nu, which is the traceless symmetric part of b mu nu. So this is done in 4 dimensions. Otherwise, I'd have a d minus 1 over here. So basically, this is telling you, so for this, you need to have more than one spatial dimension. So if you take a circle over here, it might go into an ellipse or something like that. That's the shear. And the third thing you can define is the twist, which is called omega mu nu, which is just the antisymmetric part of B. Okay, so basically this is telling you how, if the geodesic starts doing this with respect to each other. And actually we're going to take the twist to be 0. So you can show that if the congruence is hypersurface orthogonal, so if you can write xi lower mu as being proportional to d mu of some function, then this guy is 0. Okay, you guys remember that a normal to a surface defined by some function equal to 0, some function of the coordinates equal to 0, the normal is always proportional. The normal with a lower index is always proportional to d mu of that function. Okay, very good. So given this naming, then the general b mu nu is 1/3 theta times h mu nu plus sigma mu nu plus omega mu nu. And basically, one can use this geodesic deviation equation to compute the rate of changes of all of these guys. But we won't care about all of them. We're just going to care about this expansion theta. So basically, what we want to compute is d theta by d tau. Okay, which by definition is xi mu d mu theta. Still by definition it is xi mu d mu d nu xi nu. Using that. And now we're just gonna switch these two derivatives over here, and therefore pick up a Riemann tensor. Xi nu plus R mu nu nu lambda xi lambda. And now what do I want to do? So this guy is going to be equal to minus R mu lambda xi lambda xi mu. That's this guy over here, because I contracted the first and the fourth index. And the other guy, so now what I want to do is I want to pull this guy in front. So I'm going to pick up a d nu xi mu d mu C nu minus d nu C mu d mu C nu. So far it's just algebra. Now question, what is this term over here? 0, because?
The autoparallel equation.
Yeah, okay, good. I just didn't know the name. Good. And this thing over here, is just b squared, right? So this is, just to get the indices right, I guess it's b mu nu, b mu nu, something like that. I hope I got them right. B, somehow. Okay, let's hope they're right. If they're not right, you can correct it. Okay, so now basically what one can do is just plug in that particularly nice way of writing b mu nu into here to massage this equation. So basically, if you plug in that expansion, what you're going to get is minus 1/3 theta squared minus sigma mu nu plus omega mu nu minus r mu nu xi nu. Okay? Is it clear how I got it? Okay. And this thing is called Raychow-Duris equation. And it's simply just some sort of geometrical relation between how the expansion of geodesics varies as you move in tau. I mean, there's no physics in here. There's just pure geometry. But what's nice about this equation, it's basically this equation that's used very, very extensively in the use of singularity theorems. Why? Okay, so let's first get rid of this term by assuming that that the congruence is hypersurface orthogonal. Then basically what you see is happening here is that you have d theta by d tau plus 1/3 theta squared equals minus sigma squared minus r mu nu into 2 time-like vectors. And the point is that, okay, so first of all, so this term will give a negative contribution because it's minus sigma squared, whereas this term, if you use the Einstein equation to trade this r mu nu for some t mu nu of some matter fields, and then you use energy conditions, so usually matter fields satisfy energy conditions that tell you that the stress tensor into some special vectors, I mean generic, but say into time-like vectors has some certain sign. You can use those conditions to set this term to be strictly positive, so therefore with the minus is going to be negative, and then you're going to get a condition of this kind. Okay? And these kind of conditions, if you assume some initial condition on theta, they can tell you something interesting about the behavior of theta along the flow. Okay? So using this, let's discuss sort of perhaps one of the simplest singularity theorem that one can discuss, which are the cosmological singularity theorems. So for example, showing under rather mild conditions or under rather reasonable conditions that you must have a Big Bang singularity. Okay, and that thing, this thing was done by Hawking in the 60s. So okay, so let me talk about. Okay, before I talk about it, let's do the following exercise. Okay, so I'm assuming that omega is 0. I'm assuming that matter satisfies the strong energy condition. So the strong energy condition says that T mu nu, xi mu, so T mu nu matter greater or equal than -1/2 T for any time like xi mu. That's the strong energy condition. There's a lot of matter that satisfies it, so usual relativistic matter, radiation satisfies it. And by playing around with the Einstein equation, you can see that this is equivalent to this guy being positive. Should I do it, or is it clear to everybody? Should I do it?
Which one?
Sorry?
Which one did you positive?
Oh, sorry, I cannot hear you.
Which one did you say has to be positive?
Which one did I'm sorry, it's the masks, and maybe I need a... But what I'm saying is the following, that if you take, so G mu nu, the Einstein tensor is R mu nu minus 1/2 R G mu nu, right? Which is 8 pi G T mu nu. So now you do the trace reversing, right? And then you can see that R mu nu, and now let's dot it into xi mu xi nu, is precisely 8 pi G T mu nu plus 1/2 T mu, well, some appropriate number over here that will give you that equation. T G mu nu, yeah, with a minus, yeah. So xi squared is -1, yeah, so it's probably -1/2. That's what I'm saying. So the strong energy condition basically tells you that this guy is positive. Can anybody see sort of a famous form of, not matter, but cosmic ingredient that doesn't satisfy it? That doesn't satisfy that R mu nu into time-like vectors is positive? Very good. So a positive cosmological constant, which has R mu nu equals 1 or some number, some positive number over L squared G mu nu. G00 is negative, so you see that R00 is negative, so a positive cosmological constant doesn't satisfy this. But otherwise, all reasonable sorts of matter and radiation do. Okay? Very good.
Sorry, said omega mu equals to 0, what does it mean?
Sorry?
Omega mu equals to 0.
That just means that the congruence is hypersurface orthogonal. It's very reasonable. Yeah. I mean, if that's the case, you can just write, you can go to a gauge where you can write the metric as, say, minus dt squared plus a squared of t of x times the spatial part. If that's not true, then you cannot do it. Very good. So, okay, so we assume this. Okay, so under these assumptions, this thing is really negative. And now what we want to assume, so what do we want to assume? Let's start like this. If theta equals theta naught, which is negative at tau equal to 0, then theta must go to minus infinity within tau equals tau smaller or equal than 3 over modulus of theta naught. Okay, so what's happening over here? So you see that this equation is basically telling you that theta decreases with tau, right? So if you're starting with a negative value of theta, it's going to decrease. And the whole point is that one can use this equation to show that it's going to actually go to minus infinity in finite proper time. And the way to see that is trivial. What you do, you basically divide this by theta squared. And then write this as d by d tau of minus 1 over theta. So you see from here that d by d tau of 1 over theta, which is minus this guy, is going to be greater or equal than 1/3. I really hope that I write it correctly. So d of 1 over theta is d tau over 1/3 over 3. And now I integrate. So 1 over theta final minus 1 over theta naught is greater or equal than tau over 3. So you see that this guy is positive. So by the time that tau reaches 3 over modulus of theta naught, theta final will be constrained to go to 1 over theta final will have to go to 0. Okay? More interestingly, so the thing that one actually uses is that if theta equals theta naught and it's positive, then theta is going to go to infinity then theta was infinite no more than tau equals 3 over theta naught in the past. So it is clear. So now I want to actually go to the past. So since d theta by d tau is decreasing, so I'm having a positive value of theta today. And since it's decreasing, in the past it must have been larger. And exactly the same argument, but running it into the past, shows you that you must have had theta going to infinity no longer that delta tau is 3 over theta naught in the past. Is it clear what I'm doing? Okay, good. Very good. So this tells you that there's something going wrong with this congruence. By the way, since this is going to be applied to cosmology, does anybody know what theta is in a cosmological situation? So as I said, it's basically A dot over A of the spatial slices. Exactly. So theta is going to be proportional to the Hubble constant, which is of course not a constant, but yeah. Okay. Very good. So as I said, so this theta is basically A dot over A, and if you have it going to either plus or minus infinity, you see that you have two situations. You could either have dA by dt going to infinity, which really means a singularity, or you can have A going to 0, which basically means that your geodesics are crossing. So the cross area is going to 0. And that's sort of a trivial singularity. That's just a focal point. That's clearly not a problem with your spacetime. So basically, what one tries to do now is try to exclude the second possibility. Try to show that actually what's happening is that this guy that blows up, it's not that you're just having a trivial focal point. And so for that, in order to show this, so basically Hawking assumed that the spacetime is globally hyperbolic. So what that basically means is if you have some initial slice S, so you can determine the whole future evolution, and you also determine the past evolution. And in such a space-time, it is true that if you have some, how do I want to say it? Just a second. Some point P to the past of S, then every such point is connected to S by a geodesic that basically maximizes the proper time. Okay, so by a time-like geodesics, so what I want to say is the following. So as you probably know, time-like geodesics between 2 points, they maximize the proper time, right? So that's good. And then, okay, so in such a space-time, you can do this. And then, okay, once you have this kind of situation, basically you can show that this geodesic cannot have so-called, so this geodesic, okay, it's locally a geodesic, and it also sort of ends up perpendicularly to S. And this geodesic cannot have focal points, because if it did, say, if it had a focal point over here, then so you'd have some other geodesic of the same proper time connecting here to here and also perpendicular to this S. And then what would happen once you have such a focal point, you can actually, and both of them are supposed to maximize the proper time. But then you sort of get a contradiction, because if you actually round off over here, you're getting a longer proper time. Yeah, you're getting a longer proper time. And therefore, this geodesic is not proper time maximizing. Okay? So basically, all of this is to say that if you have this sort of geodesic that maximizes the proper time, cannot have focal points. If you want a simple example of where this is happening, just take a sphere. So geodesics on the sphere are just portions of the large circles. And those are the shortest paths between points if you're going sort of less than pi. If you're going more than pi, then you can have another geodesic, so you're starting to get focal points. And then this is basically telling you that there's a shorter path along the sphere which is going the other way. Okay? So trying to extend the geodesic past its focal points may make it not the shortest distance path in the case of Euclidean geodesics on a sphere, or the maximizing proper time path in the case of Lorentzian manifolds. Okay, so that's sort of the basic idea. So this geodesic cannot have focal points, but now. And okay, good. So that's the first assumption. And the second assumption is that you have this initial time slice S, and the expansion is positive everywhere, and is larger than some minimum value theta min, which is positive. Okay, so that's part of the assumption. Then the claim is that there's no path-directed time-like geodesic that you can draw that's going to have an affine length, sorry, not an affine length, a proper time greater than 3 over theta min. And the reason is, so once you start going along these geodesics, so yeah. So basically, you want to start with this idea that every point in the past is connected by a proper time maximizing geodesics. But then by this argument, using Raymaduri's equation and using the strong energy condition and so on, you know that along any such geodesic, you're going to go to theta going to infinity in finite proper time. If that thing is a focal point, then that means that geodesic is not proper time maximizing, and therefore you're contradicting the assumption that it was. therefore you arrive at contradiction. Therefore, you cannot be continuing this geodesics past their focal point. Therefore, you conclude that you're in the upper case, which is that actually you have some singularity with the space-time itself. Okay. I'm not claiming to have been extremely precise, but I hope that the sort of the main idea of the proof is.
Can you repeat the last argument?
So it's sort of a very mathematical argument by contradiction. So basically, in a globally hyperbolic spacetime, every point P, it's connected, can be connected with a proper time maximizing geodesic to the initial surface, and because it maximizes the proper time, this guy cannot have a focal point. Then you run this argument using all those assumptions, and you find that theta must be infinity, which is due to either a focal point or to a space-time singularity. If it's a focal point, you run into contradiction with this argument, so therefore it cannot be a focal point. Therefore, it's some sort of singularity. Basically, the kind of singularity that he gets is that the geodesics are inextendable. You cannot extend them past some proper time sort of shorter than this. And therefore, they must end. Why are the geodesics ending? Well, probably there's something very, very bad going on, like, for example, a Big Bang singularity. Okay, good. So, but I should say this is a sort of a, it's a very nice proof in a certain way because it assumes very little. So there's no symmetry involved, there's no nothing. All that you're assuming is some sort of geometrical condition on R mu nu, which you can sort of motivate from some sort of energy condition. So this is basically telling you if you're trying to make a cosmological, any sort of inhomogeneous, whatever, cosmological space-time in which this sort of energy condition can be cooked up to make this thing positive. And I should say, you know, there are like a zillion variations to these theorems where they assume something else and they can make matter satisfy the weak energy condition, which does allow for a positive cosmological constant, so we're sort of fine. But it's just showing you that, you know, you cannot just be playing with your matter equation and blah, blah, and get rid of the singularity. It's there, and you really have to do something non-trivial. You know, you cannot just be playing with the classical Einstein equations and get rid of the Big Bang singularity. So it's very generic, even though, as you see, this argument about the presence of the singularity, it's sort of by contradiction, it's not very easy to grasp. Okay, very good. So now what I want to do is discuss the null case. So now, the tangent vector, so again, we're considering some congruences, but now the tangent vectors are null. So k mu is 0. And therefore, there's no natural norm that you can assign. Before, we had xi squared is -1, but now we cannot set it. And so now we want to again consider this displacement vector, eta mu. And one can show that k mu, eta mu is constant along the geodesics. So, well, so I guess you just do k nu d nu of this, and you just convince yourselves of it. This was also true for the time-like guys, but we didn't discuss it. And you can set this constant to 0 to try to fix what this eta mu is, but that's not enough. And the reason that that's not enough is that you can always add to eta mu any multiple of k mu, and it still solves this condition because k squared is 0. Okay? So, so basically, the whole song and dance over here is that you want to consider equivalence classes of vectors or tensors that are defined up to this sort of arbitrary addition of k mu. And so if you have the tangent space of some point P at M, so this is the tangent space at M, so your initial manifold, then you can consider some object TP tilde, which is the space of vectors perpendicular to this k mu. So if this is a d-dimensional space, this is a d-1 dimensional one, but these are not really well defined. But what you can well define is this equivalence class, which is this TP hat, where you mod out by this relation, and this guy is a d-2 dimensional space. Okay, so just to give you an example of what you might want to do, so if k in some coordinate system is just du, so the fact that it's null, it means that GUU is 0. And then the perpendicular vectors VA satisfy, so basically satisfy KA VA, which is GUA VA equal to 0. And let's choose our A's in such a way that there's clearly that only one component of mu, sorry, what did I write? UA here. Let's choose our coordinate such that this G mu A is only non-zero for one value of A, which I'm going to call alpha. So, so different from 0 for A equals alpha. So that means basically that V alpha is 0. But we have we can consider any VU and VI different from alpha, right? Those would be perpendicular. But now, so these are basically the perpendicular vectors that live over here, but now we want to mod out by this relation. So we're going to basically mod out by this VU, which is proportional to K upper U. So we're just left with this guy with the d-2 components. Okay. I'm not going to go through it because it's a bit technical, but at the end of the day, the only thing that happens is that when you so you're basically defining the expansion, shear, and twist in sort of very similar ways, except that now your H mu nu is going to be a two-dimensional metric. And at the end of the day, actually, so these hatted tensors basically live in here, and they're just going to have hats over them. So I'm going from 3 to 2 because of, I'm really not explaining, so there's a long technical discussion in Walt if you want, but really it's, this is all that is happening. So as a consequence, your Ricciardo-Duris equation, so now tau, the proper time, is going to be replaced by the affine length along the geodesic, and this is going to become a half, and then you're going to have hats all over the place. But that's all that's happening. And now, of course, these are Ks, which are null. Okay, good. And this theta, still has the interpretation of, you know, dA by d lambda, d log A by d lambda, where A is basically the area associated to this H hat. Okay? Good. So now we want to play the same game. Basically, we want to play the same game, so we want to set the shear to 0. We want to assume that the matter satisfies the weak energy condition. Right? And as a consequence, what's going to happen is that you're going to get an equation like this. And okay. Yeah, maybe I should just write it. Wait just a second. Okay. So let me erase. Okay, good. So now let's not just do math. So as I motivated in the first part of the lecture, we want to consider these trapped surfaces. So now we're moving to the gravitational collapse situation, and we want to study these trapped surfaces, which are compact, codimension 2, smooth spade-like manifold T. So they're compact, that's important. So D minus 2 dimensional, smooth space-like manifold T, with the property that the expansion theta of both sets of future-directed null geodesics is negative. So theta is smaller than 0. So we want to assume to see what's happening once we have such a trap surface. Okay? And we're going to assume that the matter satisfies this null energy condition, which basically implies that this term is positive, and then we're looking basically at this equation with the initial condition that theta is smaller than 0. Okay. Trap surfaces. So let's call theta 0 equals the max of theta on T. Trap surface is T. Okay, I'm going to call the surface T, and I'm going to call the maximum value of the expansion theta 0, and by assumption this is negative. And then one can play with this, okay, so what should I say? Maybe I should say the claim. So the claim is that there exists at least one inextendable future-directed orthogonal null geodesic from T whose affine length is no greater with lambda smaller than 2 over theta naught. So I'm measuring lambda. I'm setting lambda equal to 0 at this point where my expansion is theta naught, which is negative. And then the claim of the theorem is that there exists at least one future-directed null geodesics perpendicular to this trap surface that cannot be extended to infinite values of its affine length, but its affine length is bounded by this number. Okay? So how does one show that? So first, it is easy to show just from this equation that if you start with theta not negative, you're going to develop theta going to minus infinity with infinite affine length. It's exactly the same argument as here. So you're integrating the equation. It's just that you have a half instead of a third. And so is this clear? Yeah. Okay. So just from Raychaudhuri's equation plus the weak energy condition plus whatever, you just get that theta goes to minus infinity within lambda smaller than 2 over theta naught. And now the whole difficult part is to show that this is not due to the formation of a focal point, but it's an actual problem that you cannot, you can really not extend this geodesic, which signals the presence of some sort of space-time singularity. Okay, and here again the argument is sort of formal. So basically, so if you remember, so in the case of the time-like geodesics, we're playing with this idea that there is any point P in the past of this initial surface is connected to it via a geodesic that maximizes the proper time. So you want some sort of analog of this maximum proper time, but for null geodesics. Of course, for null geodesics, the proper time is 0. So people come up with a concept of promptness. So basically, what promptness says is that there's no other causal curve. So if you're looking to go from some point P to some point Q, a geodesic is prompt if no other causal curve could have arrived at Q sooner than it. Okay, so you don't want to arrive in a nearby point of Q, but to the past of Q. There's no other causal curve that does that. Is it clear? And basically this forces you to have null geodesics with no focal points. The reason again being that if you had a focal point, then you have two guys. So if you have a focal point, then you have some sort of other path that is as prompt as this guy. But then you can just round off the corner and get something that arrives sooner, and therefore it's not being the fastest thing that gets to Q. There's a whole theory about this. I should mention that there's a nice set of lecture notes. So for people who are interested in the details, there's some nice set of lecture notes by Witten in 2018 at the PITP school. So he discusses these things in complete detail. If not, you can just read Wald. He also has a nice discussion. Okay, so that's the idea. Okay, so basically now what you want to consider, where should I put it here? Okay. Another comment over here that one should say is that if one is considering this point P, and one is considering the causal future of P, so this J plus of P. And then you want to consider the boundary of the causal future of P, which is this guy. Sorry, I didn't mean to draw 2 lines. Then this is going to consist of prompt null geodesics. So null geodesics with no focal points. Okay, and the same thing. So these guys are going to be prompt. And then the same thing goes if you're not starting from a point P, but from some spatial set W, you can say the same things. I'm not going into details because then it gets very, very heavy. Okay, so now we're getting closer to sort of at least the gist of the proof, which says that, so now you need some extra assumptions. So you want your spacetime to be globally hyperbolic. And it should have a non-compact initial slice S. And for, and then if you have any set C, then, okay, so this is a technical statement. The boundary of the future of C cannot be compact. And yeah, so this is again some sort of technical comment. So the idea is that if you have this C and you consider the future of C and the boundary of the future, then in a globally hyperbolic spacetime, you can basically map this guy to the initial set, to the initial surface S. And the image is going to be a submanifold of S of the same dimension of S, because the boundary of the future is codimension 1, and so is S. But you cannot have submanifolds of the same dimension. Therefore, compact submanifolds of the same dimension. Therefore, this guy cannot be compact. And now, basically, the idea of the proof is to show that the boundary of the future of the trapped surface has to be compact, and therefore you get a contradiction with this. Okay, but okay, so this is from these technical assumptions, one gets this statement, and now one looks at the trapped surface, and then okay, so one wants to consider the future. Sorry, my J's. The boundary of the future of this guy. And as we discussed, so because it's a trapped surface, then if we're, so we're starting along all the null geodesics that emanate from this surface, theta is negative initially, and we show that it's going to go to minus infinity within a fine parameter. And the reason for this, let's assume that the reason for this is a focal point. So let's assume that all the geodesics that are concerned by this are just having a focal point, and this is why the theta is going to minus infinity. In that case, they cannot be, the focal point, so in that case, so here is my T. In that case, if the focal point cannot be on the boundary of the future, because we just said that this thing has to contain only prompt geodesics, which cannot have focal points. So that means that the guys that emanate from T, their focal points, if there are, they have to do something like this. So actually the boundary of the future doesn't continue. So basically what you're getting is that, so since T is a compact surface, and this guy, if it has a focal point it has to leave the boundary of the future because it's no longer prompt, having a focal point, then this tells you that the boundary of the future of the T is actually compact. And then you're running into a contradiction with this theorem. So again, you see, it's not super intuitive. At least I didn't find it super intuitive. If Agnese looks confused, then it's really not intuitive. But I just wanted to give you an idea of what sort of goes in. So it's again a proof by contradiction, and therefore, since they cannot all be leaving this bound, yeah. Okay, therefore this cannot be happening for all of them. Therefore, there is at least one of them for which this theta goes to minus infinity is actually a singularity, and the geodesic cannot be extended. And that's inextendability of the geodesic is taken to mean a problem with the space-time itself. Was it more or less clear? I guess the goal was not to prove stuff to you, because we'd be spending 10 hours, but just give you an idea of what the idea is behind and what roughly is being proved. So any questions? Okay, so there can only be two things. Either you understood everything or you didn't understand anything. And by contradiction, it's probably the second thing. But anyways, so this was, okay, so this is roughly the idea. This is roughly the idea, so there's at least one inextendable geodesic, and therefore there's some problem with this space-time. And this problem with the space-time, as you see, it follows from very, very mild initial assumptions. So this trapped surface condition is very, very easy to check. So you don't need the full evolution. Back in that day, I guess they didn't have very powerful computers, so it was important to, to be able to check this, and then this shows to you that there's going to be some problem. But this problem, I mean, you don't know, is this a curvature singularity or is there something else going wrong? You really don't know. It really doesn't tell you what's happening. Yeah, so this thing is important because it gives this local criterion of the trap surface, which eventually tells you there's going to be some singularity. And sort of the important point is that the formation of trap surfaces is something very, very generic in gravitational collapse. So therefore, these singularities are generic, and therefore, I guess at the time it was important to show that they're not just a consequence of spherical symmetry and all of that. So once they form, you have to deal with them. And of course, once you have singularities popping out over the place, you really start worrying. So that means that of course, GR cannot describe the singularities because the limit of validity of the theory is off. So you either want GR to be able to predict anything or not. So in order for it to be able to predict, people really wanted the singularities to be hidden behind horizons. So this is where the cosmic censorship conjecture comes in. It basically tells you not that naked singularities don't exist. You can certainly have naked singularities, but they don't form from generic initial data. You can also have non-generic initial data, highly finely tuned, that do form naked singularities, but that's not what happens generically. You can convince yourself, so I guess in the early days, people convinced themselves of this genericity by just slightly perturbing some black holes or some collapse situations and seeing that actually the perturbations die off and stuff like that. So that tells you that the formation of the singularity is a stable feature. And as I said, this is this singularity theorem it's extremely important observationally because until LIGO, basically this was the only way that people knew that you have black holes once your mass is past 3m. And the question that follows, okay, so you have these black holes that form generically in gravitational collapse, and you want to know, what you want the classification of these black holes. Well, what are the most general, equilibrium states that you can get for these black holes? And as far as I understand, so there was some paper in '67 by, so this stuff is like 65, 66, something like that. And there was a paper in '67 by Israel. So I mentioned the Birkhof Theorem, which shows that once you have spherical symmetry, you get staticity using Einstein's equations. Israel showed that if you have staticity, you have spherical symmetry. And that's a huge constraint on the solution. And actually, okay, so I don't have time to do anything anymore. So I thought of, so there's some nice lecture notes from '72 at Les Ouches, where all these people were lecturing. And if my tablet ever works, which is difficult. So I just wanted to read to you. So Carter was also giving some lectures on, and he also has a little like historical note. And it was really cute to read what people thought about black holes back in the days, because we know so much stuff about them, and we have so many priors. So he's talking about Israel's result. So they were blah, blah, blah. So they had all these singularity theorems. They had the cosmic censorship. So they were trying to understand these black holes better now that they were relevant. However, in that year, a new result was announced by Israel, which took me, and as far as I know, everyone else in the field by surprise. Despite the, this was the theorem which could be taken, subject to some fairly obvious assumptions, which have been since fully justified, as implying that the Schwarzschild solution is the only possible pure vacuum exterior solution for a stationary black hole, which is non-rotating. Until then, I think that we all had thought of a black hole, even in the stationary limit, as potentially a fairly complicated object. I know that I had always imagined it should have many internal degrees of freedom, representing the vestigial multiple structure of the star or other object from whose collapse it had arisen. Yet, so basically they thought that the black holes were a bit like planets, they had mountains and stuff, and now they were very, very shocked to see that they had to be spherically symmetric. Yet here was a theorem which implies that if rotational effects were excluded, there could be no internal degrees of freedom at all, apart from the mass itself. My immediate reaction, and as far as I can remember this how Israel himself saw the situation, was to suppose that this meant that only stars starting off with artificially restricted multiple structures, and in the non-rotating case only exactly spherical stars, could form black holes with well-behaved event horizons, so that the natural outcome of a gravitational collapse under physically realistic conditions would always be the formation of a naked singularity. In short, it seemed that the cosmic censorship conjecture was utterly erroneous, and that our work on black hole theory had been, from a physical point of view, rather a waste of time. So this state of alarm did not last very long. However, since in the discussion that followed, in which Roger Penrose took the leading part, it soon became clear that there was an almost diametrical opposite. So they understood that actually the black hole just radiates away all the multiple moments, and then the final, which made sense, and then it leaves a final equilibrium state, which is rotationally symmetric. But I thought this was cute because it had never, having heard always the uniqueness theorems, I had always, I had never thought of a black hole as a planet, but apparently, if you have no priors, this is what you're supposed to think. So, okay. So this uniqueness theorem, so you have for static, you get spherical symmetry, and for stationary, you get axis symmetry. So in 4 dimensions, the only possibilities are the Schwarzschild and the Kerr black hole. And this sort of no-hair property of the black holes, the fact that you don't have any internal degrees of freedom, or basically the starting point for the whole subject of black hole thermodynamics, because you start wondering, okay, if I start throwing in objects and, the only thing that changes is the mass, you know, what's happening to my entropy. Okay, good. So, so that was it. I hope, so next, tomorrow we're going to actually start into black hole thermodynamics, but I just wanted to show this. It's a bit technical, but I think it's important to see where and why this is generic and why this is important. Questions? Yeah, so if anybody wants to ask questions about this and the previous, I'm here. And also online people, the online people.